The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
So far we've seen things about vectors, equations of planes, motions in space, and so on. Basically, we've done geometry in space. But calculus really is about studying functions. So now we are going to actually move on to studying functions of several variables. So this new unit, what we'll do over the next 3 weeks or so, will be about functions of several variables and their derivatives. Okay? So first of all, we should try to figure out how we are going to think about functions. So remember, if you have a function of one variable, that means you have a quantity that depends on one parameter. Maybe f depends on a variable x. And for example, the function that you all know is f of x equals sine x. And the way we would represent that is using maybe by plotting the graph of a function. So the graph of a function, we plot y equals f of x. And in the case of a sine function, that looks like this. Okay. So now, let's say that we have actually a function of two variables. So that means that the value of f depends actually on two different parameters. Say, maybe the variables are x and y, or they could have any names you want. Okay, so given values of the two parameters x and y, the function will give us a number that we'll call f of xy that depends on x and y according to some formula. Okay, not very surprising so far. So for example, I can give you the function f of xy equals x squared plus y squared. And of course, as with functions of one variable, we don't need things to be defined everywhere. Sometimes there's a domain of definition. So this one is defined all the time. But if I tell you, say, f of xy equals square root of y, well, this is only defined if y is non-negative. Or if I tell you f of xy equals 1 over x plus y, well, that's only defined if x plus y is not 0, and so on. Okay. Now, so these are, mathematical examples given by explicit formulas. And of course, there's physical examples, or examples coming from real life. For example, you can look at, the temperature at a certain point on the surface of the Earth. So you use maybe longitude, latitude, that's x and y. And then you have f of xy equals the temperature at that point. Or in fact, because temperature depends also maybe on how high up you are, it depends on elevation. So it's actually a function of maybe x, y, z. And it also depends on time. So in fact, maybe it's a function of t for time, x, y, z coordinates in space. So you see that real-world functions can depend on a lot of variables. So our goal will be to understand how to deal with that. Okay, so Now, you'll see very soon that actually it's already tricky enough to picture a function of two variables. So we're going to focus on the case of functions of two variables. And then we'll see that if we have more than two variables, then it's harder to plot the function. We cannot draw what the graph looks like anymore. But the tools are the same. The notion of partial derivatives, gradient vector, and so on, all the tools that we will develop work exactly the same way, no matter how many variables you have. So I'll say, for simplicity, we'll focus mostly on two, or sometimes three, variables. But it works the same in any number of variables. OK, so the first question is, how do we visualize a function of two variables? So the first thing we can do is try to draw the graph of f. So maybe I should say f, which is a function of two variables. So the first answer will be we can try to look at its graph. And the idea is the same as with one variable. Namely, we look at all the possible values of the parameters x and y. And for each of them, we plot a point whose height is the value of a function at these parameters. So we'll plot, let's say, z equals f of xy. And now that will become actually a surface in space. Okay, so for each value of x and y, here we have xy in the xy plane. Then we'll plot the point in space at position xy and z equals f of xy. Okay, and if we take all of these points together, they will give us some surface that sits in space. Yes? Oh, a function of two variables. Shorthand. Well, let's say how to visualize a function of two variables, if you want. OK? So how do we do that concretely? Say that I give you a formula for f. How do we try to represent it? So let's do our first example. Let's say that I give you the function f of xy equals negative y. Okay? So I mean, it looks a little bit silly because it doesn't depend on x, but that's not a problem. It's still a valid function of x and y. Just happens to be constant with respect to x. So to draw the graph, we look at the surface in space defined by z equals minus y. What kind of surface is that? It's a plane, OK? And if we want to draw it, z equals minus y, we'll look, well, that's the y-axis, that's the x-axis, that's the z-axis. If I look at what happens in the yz plane, in the plane of a blackboard, it will just look like a line that goes downward with slope 1. Okay, so it will do this. And what happens if I change x? Well, if I change x, nothing happens because x doesn't appear in this equation. So in fact, if instead of setting x equal to 0, I set x equal to 1, I'm in front of a blackboard, or minus 1 at the back, well, it still looks exactly the same. So I have this plane that actually contains the x-axis and slopes downwards with slope 1. It's kind of hard to draw. Now you see immediately what the big problem with graphs will be, that these pictures are hard to read. So that's our first graph. Okay, any questions so far? No? Okay, so let's say that we have a slightly more complicated function. How do we see it? So let's do another example. Let's say I give you f of xy equals 1 minus x squared minus y squared. So we should try to picture what the surface z equals 1 minus x squared minus y squared looks like. So how do we do that? Well, maybe you're actually very fast and you've already figured out what it looks like. But if not, then we need to work piece by piece. So maybe it will help if we understand first what it does in the plane of a blackboard. Okay? So if we look at it in the yz plane, that means we set x equal to 0. And then z becomes 1 minus y squared. What is that? It's a parabola pointing downward and starting at 1. Okay? So we should draw maybe this downward parabola. It starts at 1 and it cuts the y-axis at 1. Okay? When y is 1, that gives us 0. What do we see? Let's, so we might have an idea of what it might look like, or maybe not. Let's get more slices. Let's see what it does in the xz plane, this other vertical plane that's coming toward us. So in the xz plane, it means we set y equal to 0, and we get z equals 1 minus x squared. It's again a parabola coming downward. Okay, so I'm going to try to draw a parabola that goes downward, but now to the front and to the back. So we are starting to have a slightly better idea, but we still don't know whether the cross-section of this thing might be, round, square, something else. So if we want more confirmation, we might want to also figure out maybe where does this surface intersect the xy plane. So we hit the xy plane when z equals 0. That means 1 minus x squared minus y squared should be 0. That becomes x squared plus y squared equals 1. That is a circle of radius 1. Okay, that's the unit circle. So that means that here we actually have the unit circle. And now you should imagine that you have this thing that, when you slice it by a vertical plane, looks like a downward parabola, and it's actually a surface of revolution. You can rotate it around the z-axis. Okay? Now, if you stare long enough at that equation, you'll actually see that, yes, actually, a posteriori, we know that it had to be like that. But see, so these are useful ways of trying to guess what the graph looks like. Of course, the other way is to just ask your computer to do it, and then, you'll get that kind of formula. Okay. Well, I can leave it on if you want, but no, because I plotted a different function that I will show you later. So it goes this way. If you want 1 minus, it's really going downward. Yes, I agree that the sheet is upside down, but that's because I plotted something else. Okay. So, in fact, well, so what I plotted in my computer was actually x squared plus y squared. That looks like that. See, it's the same with a parabola going upwards. If you want to see more examples, I have various examples to show. Well, here's the graph of a function y squared minus x squared. See, so that one is kind of interesting. It looks like a saddle. If you look at it in the yz plane, then it's a parabola going up, z equals y squared. And that's what we see to the left and to the right. But if you put it in the xz plane, then it's a parabola going downwards, z equals minus x squared. So we have a parabola going downwards in one direction, upwards in the other one, and together they form this surface. And of course, you can plot, much more complicated functions. So this one I well, if you can read very small things, then you can see the formula, but it doesn't matter, just to show you that you can put the formula into a computer, and it will show you a picture. OK. So that's pretty good, but I mean, you can see that it can get a bit cluttered, because maybe there's features that are hidden behind, or maybe we have trouble seeing. If we don't have a computer, that looks very readable, but this is kind of hard to visualize sometimes. So there's another way to plot functions of two variables, and that's called the contour plot. So the contour plot is a very elegant solution to the problem that it's difficult to draw space pictures on a sheet of paper or on a blackboard. So instead, let's try to represent a function of two variables by just a map. The same way that when you walk around, you have actually geographical maps that fit on a piece of paper that tell you about what the real world looks like. So what a contour plot looks like is something like this. So it's an XY plot, and on it you have a bunch of curves. And what the curves represent are the elevations on the graph. So for example, this curve might correspond to all the points where f of xy equals 1. And that curve might be all the points where f equals 2 and f equals 3, and so on. Okay? So when you see this kind of plot, you're supposed to think that the graph of a function is, somewhere sits in space above that. It's like a map telling you how high things are. And, what you would want to do with a function really is be able to tell quickly what's the value at a given point. Well, let's say that I want to look at that point. I know that f is somewhere between 1 and 2. Actually, it's much faster to read than the graph. On the graph, I might have to look carefully and then measure things and so on. Here, I can just read the value of f by comparing with the nearby lines. OK, so let me try to make that more precise. So this shows all the points. Where f of xy equals some fixed values, some fixed constants. And these constants typically are chosen at regular intervals. So for example, here I chose 1, 2, 3, and I could continue with 0, -1, and so on. So one way to think about it, how does this relate to the graph? Well, that's the same thing as cutting, or maybe I should say we slice, the graph by horizontal planes. So horizontal planes have equations of the form z equals some constant, z equals 0, z equals 1, z equals 2, and so on. So maybe the graph of my function will be some sort of blob out there. And if I slice it by the plane z equals 1, then I will get the level curve, which is the points where f of xy equals 1. And so that's called a level curve of f. Okay, and so we repeat the process with maybe z equals 2, and we get another level curve, and so on. And then we squish them all on the map, and that's how we get the contour plot. Okay, so each of these lines, imagine that this is like some mountain or something that you're hiking on. Each of these lines tells you how you could move to stay at a constant height. If you want to get to the other side of a mountain, but without ever going up or down, you just walk along that path. And it will get you there without effort. So in fact, I've been talking about hiking on mountains, well, that's exactly what a topographical map is about. Sorry, so I need to zoom a bit. So a topographic map, this one is from the US Geological Survey, shows you basically all the level curves of the altitude function on a piece of land. So you know that if you walk along these curves, you will stay at the same height. And you know that if you walk towards, these don't have numbers. Here, let me find a place with numbers. Here, there's a 500 in the middle. So you know that if you walk on the line that says 500, you stay always at 500 meters in elevation. If you walk towards the mountain that I think is below it, then you will go up, and so on. So you can see, for example, here, there's a peak, and while here there's a valley with actually the river in it, and the altitudes go down and then back up again on the other side. Okay, so that's an example of a contour plot of a function. Of course, we don't have a formula for that function, but we have a contour plot. And that's what we need, actually, to understand what's going on there. OK, any questions? No? OK, so another example of contour plots. Well, you've probably seen various versions of these temperature maps. So that's supposed to be how warm it is right now. So this one is color-coded. Instead of having curves, it has all of these colors, but the effect is the same. If you look at the separations between consecutive colors, these are the level curves of a function that tells you the temperature at a given point. Okay, so these are examples of contour plots in real life. Okay, no questions? No? Okay, so basically one of the goals that one should try to achieve at this point is becoming familiar with the plot, the contour plot, the contour plot, the graph, and how to view and deal with functions. Oh. Uh-oh. Okay. So let's do an example. Well, let's do a couple of examples. So let's start with f of xy equals minus y. I'm going to take the same two examples as there to start with, so that we see really the relation between the graph and the contour plot. So let's try to plot it. So where's the level curve f equals 0 for this one? Well, f is 0 when y is 0. So that's the x-axis. Okay, so that's the level 0. Where's the level 1? Well, f is 1 when negative y is 1. That means when y is negative 1. So I'll go to minus 1, and that will be where my level 1 is. And so on. F is 2 when y is negative 2. F is negative 1 when y is 1, and so on. Okay? Is that convincing? Do you see how we got that? Okay, let me do it again. I don't see anybody nodding, so that's kind of bad news. So if I want to know where's the level curve, say 1, I try to set f equal to 1. Let's do this one. F equals 1 means that negative y is 1, means that y is minus 1, and y equals minus 1 is this horizontal line on this chart. Okay. And same with the others. So you can see on this map that the value of a function doesn't depend on x. If you move parallel to the x-axis, nothing happens. If you move in the y direction, it decreases at a constant rate. That's why the contours are evenly spaced. See, how spaced apart they are tells you actually how steep things are. So that corresponds exactly to that picture, except that here we draw x coming to the front and y to the right, so you have to rotate the map by 90 degrees to get to that. It's an unfortunate consequence of the usual way of plotting things in space. Okay, so these horizontal lines here correspond actually to horizontal lines here. Okay. Second example, let's do 1 minus x squared minus y squared. Okay? Or maybe I'll rewrite it as 1 minus x squared plus y squared. It's really the same thing. So x, y, let's see, where is this function equal to 0? Well, we said f is 0 on the unit circle. Okay, so the 0 level, well, let's say that this is my unit. That's where it's 0. What about f equals 1? Well, that's when x squared plus y squared equals 0. Well, that's only going to be here. So, that's just a single point. What about f equals minus 1? That's when x squared plus y squared equals 2. That's a circle of radius square root of 2, which is about 1.4. So it's somewhere here. Then negative 1. Minus 2, similarly, will be x squared plus y squared equals 3. Square root of 3 is about 1.7. And then minus 3 will be of radius 2, and so on. So what I want to show here is that, so that's minus 3, that's minus 2. What I want to show here is that they're getting closer and closer apart. Okay? So first, it's concentric circles that tells us that we have a shape that's a solid of the graph is going to be a surface of revolution. Things don't change if I rotate. And second, the contour, the level lines, the level curves are getting closer and closer to each other. That means it's getting steeper and steeper because I have to travel a shorter distance if I want my altitude to change by 1. Okay, so this top here is kind of flat, and then it gets steeper and steeper. And that's what we observe on that picture there. Okay? So just to show you a few more, where did I put my... So for x squared plus y squared, the contour plot looks like this. Maybe actually I'll make it. Okay, so it looks exactly the same as this one, but the difference is if you can see the numbers, which are not there, so you can see them, then you would know that instead of decreasing as we move out, this one is increasing as we go out. Okay, so that's where we use actually the labels on the level curves that tell us whether things are going up or down. But the contour plot looks exactly the same. For the next one I had, I think, was y squared minus x squared. So the contour plot, well, let me actually zoom out. So the contour plot looks like that. So the level curve corresponding to 0 is actually 2 diagonal lines. And if you look on the plot, say that you start at the saddle point in the middle, and you try to stay at the same level. So it looks like a mountain pass, right? Well, there's actually 4 directions from that point that you can go staying at the same height. And they actually, on the map, they look exactly like these 2 crisscrossing lines. Okay, so these are things that go on the side of the 2 mountains that are to the left and right. and stay at the same height as the mountain pass. On the other hand, if you go along the y direction, to the left or to the right, then you go towards positive values. And if you go along the x-axis, then you get towards negative values. Okay. The equation for the function was y squared minus x squared. Okay. So you can try to plot them by hand and confirm that it does look like that. But I trust my computer. And finally, this one, well, so the contour plot looks a bit complicated, but you can see two things. In the middle, you can see these two regions with these concentric circles. Actually, they're not really circles, but these closed curves that are concentric, and they correspond to the two mountains. And then, at some point in the middle, we have a mountain pass, and there we see the two crossing lines again, like on the plot of y squared minus x squared. And so, at this saddle point here, if we go north or south, then we'll go down on either side to the valley. And if we go east or west, then we'll go towards the mountains. We'll go up. Okay? Does that make sense a little bit? Okay, so reading plots is not easy, but hopefully we'll get used to it very soon. Okay, so actually let's say, okay, so I want to point out one thing. The contour plot tells us actually what happens when we move, when we change x and y. So if I change the value of x and y, that means I'm moving east, west, or north, south on the map. And then I can ask myself, does the value of a function increase or decrease in each of these situations? Well, that's the kind of thing that the contour plot can tell me very quickly. So okay, so say, for example, that I have a piece of contour plot that looks like that. Maybe this is f equals 1, and this is f equals 2, and here this is f equals 0. And let's say that I start at a point, say at this point. Okay, so here I have x0, y0, and the question I might ask myself is, if I change x or y, how does f change? Well, the contour plot tells me that if x increases and I keep y constant, then what happens to f of xy? Well, it will increase, because if I move to the right, then I go from 1 to a value bigger than 1. I don't know exactly how much, but I know that it's somewhere between 1 and 2. It's more than 1. If x decreases, then f decreases. Okay? And similarly, I can tell that if y increases, then f, well, looks like if I increase y, then f will also increase. And if y decreases, then f decreases. And that's the kind of qualitative analysis that we can do easily from the contour plot. But maybe we'd like to actually be more precise than that and tell how fast f changes if I change x or y. Okay? So to find rates of change, that's exactly where we use derivatives. So we are going to have to deal with partial derivatives. So I will explain to you soon why partial. So let me just remind you first, if you have a function of one variable, then, so let's say f of x, then you have a derivative, f prime of x is also called df dx, and it's defined as a limit when delta x goes to 0 of the change in f. Sorry, it's not going to fit. I need to go to the next line. It's going to be the limit as delta x goes to 0 of the rate of change. So the change in f between x and x plus delta x divided by delta x. Okay, sometimes you write delta f for the change in f divided by delta x. Then you take the limit of this rate of increase as delta x goes to 0. Now, of course, if you have a formula for f, then you know, at least you should know, I suspect most of you know, how to actually take the derivative of a function, from its formula. So now, how do we do that? Oh, sorry, and I should tell you also what this means on the graph. So if I plot the graph of a function, and I have my point x, and here I have f of x, how do I see the derivative? Well, I look at the tangent line to the graph, and the slope of the tangent line is f prime of x. Okay? And truth in advertising, not every function has a derivative. You have functions that are not regular enough to actually have a derivative. So in this class, we are not going to actually worry too much about differentiability, but it's good at least to be aware that you can't always take a derivative. So yes, and what else do I want to remind you of? Well, we also have an approximation formula. Which says that, if we have the value of f at some point x0, and then we want to find the value at a nearby point x close to x0, then our best guess is that it's f of x0 plus the derivative f prime at x0 times delta x, or if you want, x minus x0. Okay? Is this kind of familiar to you? Yeah, I mean, maybe with different notations. Maybe you called that delta x or something. Maybe you called that x0 plus h or something. But it's the usual approximation formula using the derivative. If you put more terms, then you get the dreaded Taylor approximation that I know that you guys don't like. So, okay. So the question is, how do we do the same for a function of two variables, f of x, y? So the difficulty there is we can change x, or we can change y, or we can change both. And presumably, the manner in which f changes will be different depending on whether we change x or y. So that's why we have several different notions of derivative. So we have a notation. Okay, so this is a curly D, and it is not a straight D, and it is not a delta. It's a D that kind of curls backwards like that. And the way you read this symbol is partial. Okay, so it's the special notation for partial derivatives. And essentially what it means is we are going to do a derivative where we care about only one variable at a time. That's why it's partial. It's missing the other variables. Okay, so a function of several variables doesn't have a usual derivative. It has only partial derivatives for each variable. So the partial derivative, df partial f partial x at x0, y0 is defined to be the limit when I take a small change in x, delta x, of the change in f divided by delta x. Okay, so here I'm actually not changing y at all. I'm just changing x and looking at the rate of change with respect to x. And I have the same with respect to y. Partial f partial y is the limit, so I should say at a point x0, y0 is the limit as delta y tends to 0 of, so this time I keep x the same, but I change y. Okay, so that's the definition of a partial derivative. And we say that a function is differentiable if these things exist. Okay, so most of the functions we'll see are differentiable, and we'll actually learn how to compute their partial derivatives without having to do this. Of course, we'll just use the usual methods for computing derivatives. So in fact, I claim you already know how to take partial derivatives. So let's see what it means geometrically. So geometrically, my function can be represented by its graph. And I fix some point x0, y0. And then I'm going to ask myself what happens if I change the value of, well, if I change the value of x, keeping y constant. So if I keep y constant and change x, it means I'm moving forward or backward parallel to the x-axis. So that determines for me a vertical plane, okay, parallel to the xz plane when I fix y equals constant. And now if I slice the graph by that, I will get some curve that goes, it's a slice of the graph of f. And now what I want to find is how f depends on x if I keep y constant. That means it's the rate of change if I move along this curve. So in fact, if I look at the slope of this thing, so if I draw the tangent line to this slice, then the slope will be partial f over partial x. I think I have a better picture of that somewhere. Yes, here it is. Okay, that's the same picture, just with different colors. So I take the graph, I slice it by a vertical plane, I get a curve, and now I take the slope of that curve, and that gives me the partial derivative. And to finish, let me just tell you how, sorry, and I should say partial f partial y is the same thing, but slicing now by a plane that goes in the yz directions. Okay, so I fix x equals constant. That means I slice by a plane that's parallel to the blackboard. I get a curve, and I look at the slope of that curve. Okay, so it's just a matter of forgetting one variable, setting it constant, and looking at the other one only. So how to compute these things? Well, we actually, to find, oh, there's a piece of notation I haven't told you yet. So another notation you will see, I think this is what one uses a lot in physics, and this is what one uses a lot in applied math, which is the same thing as physics, but with different notations. Okay, so there's two different notations, partial f, partial x, or f subscript x, and they're the same thing. Well, we just treat y as a constant and x as variable. And vice versa if we want to find partial with respect to y. So let me just finish with one quick example. Let's say that I give you f of x y equals x cubed y plus y squared. Then partial f partial x, well, let's take the derivative. So here it's x cubed times a constant. Derivative of x cubed is 3 times x squared times the constant, plus what's the derivative of y squared? 0, because it's a constant. If you do instead partial f partial y, then this is actually a constant times y. The derivative of y is 1, so that's just x cubed. And the derivative of y squared is 2y. Okay, so it's fairly easy. You just have to keep remembering which one is the variable, which one is not. Okay, so more about this next time, and we'll also learn about maxima and minima in several variables.